Hello, in this video I'll be discussing how to draw Lewis structures and how to calculate formal charge for them. So Lewis structures are basically just the way we draw molecules and compounds in chemistry. It's a universal method that we can use to show what these things look like at the superficial level. And chances are you've seen many Lewis structures before in your life. I find it very unlikely that you've never seen a Lewis structure. And Lewis structures are incredibly important, particularly if you go on to study organic chemistry. So I know many Gen Chem students eventually go on to take organic chemistry for one reason or another. And I will say this, mastering the art of drawing Lewis structures and of correctly calculating formal charge is a vital skill in organic chemistry. So you'll be much better off if you master how to do this now. That way when you get to organic chemistry, you'll know what you're doing. Because drawing Lewis structures is essentially the basis of organic chemistry. So master this stuff now, get good at it now, practice it now, because formal charge and Lewis structures become essential tools for the rest of chemistry and even into biology. So it's very, very important. So there are some rules and conventions that sort of dictate how we think about Lewis structures. So this big one right here is the octet rule. And essentially the octet rule states that certain p block elements, so I'm thinking of elements on the p block, which is, remember, is on the right side of the periodic table, they are at their most stable when they have 8 electrons around them. I'm thinking specifically about elements like nitrogen, carbon, oxygen, halogens. Those definitely feel the most stable when they have 8 electrons around them. And that's sort of the basis of covalent bonding. So you'll 99% of the time see Lewis structures involved with covalent structures. Ionic bonds have Lewis structures, but they look very different. They're bracketed structures showing donation of electrons versus what we think of as Lewis structures with the lines and the dots. That is more specifically covalent bonding at work. So for the octet rule, those certain p block elements are sharing electrons with one another, and ultimately they're going to share electrons in a way that allows them to have at least 8 electrons around them. And for certain elements, they can't have any more than 8. So for elements, carbon, nitrogen, oxygen, fluorine, they cannot exceed 8 electrons around them. You cannot break the octet rule with those 4 elements. Now, you can do it with elements beyond the third period, the third row, and those are elements that can actually violate the octet rule. So once you get beyond row 3, you can have what are called expanded octets. And that's because beyond the third row, you have d orbitals. And when you have d orbitals, you have places that you can put extra electrons. So it's kind of like adding extra shelves to a bookcase. You know, when you get to the third row, you can start putting your extra electrons into the d orbital. You can't do that with the second row and the first row. So they are bound to the octet rule. And I will say, usually you want to calculate formal charge before you finalize your Lewis structure. Because your formal charge is going to allow you to understand what exactly is going on in terms of, okay, do I put a double bond here? Do I put a single bond here? How many lone pairs do I need? So formal charge is really going to help dictate what your Lewis structures look like. And you want to use proper bonding patterns. And I'll show you in just a second that certain elements have specific patterns that you normally see them take when they bond with other elements. So there's certain patterns that you'll see come up over and over and over again, and as you get more and more practice drawing Lewis structures, a lot of those patterns will just become second nature, because you'll just know how to do them at a certain point. So practice these a lot, practice, 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 and I promise that you'll start to see the patterns emerge, and you'll start to see certain conventions that will, in the future, you won't even think twice about doing them. You'll just think about doing them. Particularly in organic chemistry, you'll just start drawing things based on how you know how to draw them versus any formal thinking about what they look like. So there's sort of notation involved with Lewis structures, particularly with bonding. So remember, with bonding, we want to show two elements covalently bonded to each other with a line. And that line is going to represent the two electrons that are shared between those two elements. So a single bond is represented by a single line. And this line is going to represent both of those electrons that are shared between those two elements. A double bond is going to represent two lines, and these two lines represent 4 electrons that are shared between those two elements. So remember, there's 2 electrons per line. And triple bonding, same principle. 2 electrons per line, which means there's a total of 6 electrons represented in a triple bond. And remember, those 2 electrons are shared between both elements. So both elements are going to get in on that electron action. And then besides lines, we also have dots, which are called lone electrons. And lone electrons are most typically found with lone pairs. So this right here, these 2 electrons here, would be known as a lone pair. And lone pairs are going to be around certain elements where you're going to see maybe a single bond and the rest of them are lone pairs, or you'll see a double bond and the rest of the electrons are lone pairs. So lone pairs are typically the last thing I do in a Lewis structure, because it's only at that point, once you figure out all the bonding patterns, that you can start filling in the lone pairs at your discretion. So now I'm going to go ahead and write out some of the common bonding patterns that you see for some of the more common elements that you see when you're drawing Lewis structures in Gen Chem, and later on also for organic chemistry as well. Okay, so here are some of the more common bonding patterns that you'll see with Lewis structure drawing. So for hydrogen, hydrogen can only have 2 electrons around it at any time. So hydrogen is an exception to the octet rule because hydrogen cannot have more than 2 electrons. So 2 electrons represents a full set for hydrogen. So hydrogen is most commonly going to be single bonded to something else. I can't think of really any time when hydrogen is doing more than single bonding with another element. It just doesn't happen. For carbon, so carbon is basically the Mac Daddy for bonding. Carbon loves bonding, and that's why carbon is basically the element of life, because it bonds so readily with several other P block elements and hydrogen. So carbon is really a major player with bonding, and you'll see carbon all over the place. And it has several different common bonding patterns. It can have 4 single bonds. It can have 2 single bonds and a double bond. It can have 2 double bonds. It can have a triple bond and a single bond. The one thing with carbon, though, is that carbon almost never wants to take a lone pair. Carbon hates lone electrons. It wants to be bonded to something. If it can find an excuse to be bonded to something, it's going to be bonded to something. So really the only time I can think that carbon has a lone pair is in the cyanide ion. So other than the cyanide ion, carbon almost always is going to have bonded electrons rather than lone pairs. Nitrogen has 2 main bonding patterns. 3 single bonds with a lone pair and a triple bond with a lone pair. And that's because these bonding patterns minimize the formal charge for nitrogen. That's why you see nitrogen take these forms so often, because these forms minimize the formal charge of nitrogen. And you always want to minimize formal charge when you can for elements in Lewis structures. Oxygen and sulfur, because they're in the same group, they're just one element apart going up and down, they also share similar bonding patterns. So you're going to see 2 single bonds with 2 lone pairs and a double bond with 2 lone pairs. Same thing with sulfur, commonly at least. And that's because these bonding patterns minimize formal charge. So these bonding patterns just don't come out of anywhere. They exist because they help to minimize the formal charge. That's why you see these commonly in different compounds. And for the halogens, so remember the halogens are group 7A, from fluorine down to iodine. And they exhibit this very common bonding pattern for the halogens, which is a single bond with 3 sets of lone pairs around the element. And that's because this also minimizes the formal charge. So we'll talk about formal charge in just a second. So take note of these common bonding patterns. You might want to write them down. You might want to be familiar with them because they'll help you when you think about drawing your Lewis structures. Okay, what would this normally look like? These bonds are what these elements normally look like when they're in a Lewis structure. So think about the common patterns when you go to decide what your final Lewis structure would look like. Okay, so formal charge is going to be calculated by taking the number of valence electrons for your element, subtracting the number of bond lines around the element, so not bonds as in one single bond, one double bond, but the total number of bond lines, minus the number of lone electrons. Not lone pairs, but total lone electrons. So if you have a lone pair, that would consist of 2 lone electrons. Just take the number of valence, minus the number of bond lines, minus the number of lone electrons, and that gives you formal charge. Now you want to minimize formal charge, which means you want the formal charge to be as close to 0 as possible. And that's going to dictate what your final Lewis structures look like. So minimize formal charge, and if you have to have a negative formal charge on something, have it be on the more electronegative atom. So remember that electronegativity increases to the right and increases as you go up the periodic table. So it's similar in a way to electron affinity. So make sure you're considering that when you're drawing your Lewis structures, and always calculate the formal charge, especially when you're first starting into your Lewis structure practice. So let's start with a basic element, and we'll do a few that are sort of progressively more difficult. So let's say we wanted to draw the Lewis structure of hydrochloric acid, HCl. Well, first thing we want to do is remember our common bonding patterns. But before we do that, calculate the total number of electrons for your compound. So remember, hydrogen has a valence electron of 1, it just has 1 valence electron, and chlorine has 7 valence electrons. So that's going to be a total of 8 electrons that we need to represent in this Lewis structure. All your electrons have to be represented in your Lewis structure. You have to find a way to do that. In some ways you have to use some tricks to be able to do that, but always make sure you go back and count all of your electrons because they all need to be there. So let's think about our common bonding patterns. Well, we know hydrogen usually single bonds to an element, and we know chlorine, which is a halogen, also usually single bonds to an element. So this is a pretty good match made in heaven because these two are probably very compatible in that regard because they're both used to single bonding. And now that we've got this, which is called the skeleton structure, which lacks lone pairs, we can go in and fill the lone pairs. So remember that we normally see halogens with 3 sets of lone pairs, and hydrogen doesn't need any lone pairs. So now let's count our total number of electrons. Remember, this single bond represents 2 electrons. Each of these lone pairs represents 2 electrons, so 2, 4, 6, 8. We have our total number of electrons. Let's make sure our formal charge is minimized, however. So what you might want to do is pause the video, calculate the formal charge for both hydrogen and chlorine in this instance, and make sure they're both 0, or minimized, close to 0 as possible. Okay, so for hydrogen we have 1 valence electron minus 1 bond line minus 0 lone pairs equals a formal charge of 0. Same thing for chlorine. So for chlorine we have 7 valence electrons minus 1 single bond minus 6 lone electrons equals a formal charge of 0. So for this next compound, sulfuric acid, H2SO4, I've went ahead and drawn the skeleton structure. Now this represents an oxyacid, and for oxyacids, whenever you have the oxygens at the end of the compound and hydrogens at the beginning of the compound, those hydrogens are going to be bonded to the oxygens. So that's something important that you'll need to keep in mind. Whenever you have hydrogens out front and oxygens at the end, the hydrogens are going to be bonded to those oxygens, or at least some of the oxygens. So right here we're showing the hydrogens bonded to the oxygens, not the central atom. You'll almost never see the hydrogen actually bonded to the central atom. It's almost always going to be bonded to the oxygens in question. So let's look at the total number of electrons for this structure. So there's a total of 32 electrons in this structure. Sulfur and oxygen both have 6 valence electrons, so 4 oxygens in a sulfur, that's 6 times 5, which is 30, and then 1 valence electron for each hydrogen, that's 2, for a total of 32. So we need 32 total electrons represented in this Lewis structure. So for these two oxygens, see how we have that common bonding pattern where we have 2 single bonds? So that lets us know that we can go ahead and fill in these 2 lone pairs. Right? Because we know that's common to oxygen. So now oxygen has a full octet. This oxygen has a full octet. So these 2 oxygens are fine. We can leave them alone. What about these 2 oxygens? Well, right now, both of these oxygens would have a negative formal charge because they only have a single bond, and we would end up putting 3 sets of lone pairs around them. That's not very good because this isn't a negatively charged compound. So go ahead and stick a double bond and see what happens. So now that we've stuck a double bond on that, put some lone pairs on it, like that, and all of a sudden both of these oxygens now have a full octet. But what about sulfur? Right now we're showing sulfur with more than 8 electrons around it. Is that okay? Yes, because sulfur is in row 3, and we know that elements beyond row 3 can accommodate expanded octets. And just to make sure you believe me on that end, I went ahead and did the formal charge calculation for sulfur in this case. So sulfur has 6 valence electrons minus 6 bonds. Remember, bond lines, so 2, 3, 5, and 6. So 6 bond lines minus 0 lone pairs equals a formal charge of 0. So every element in this compound has a formal charge of 0, which it should. So we've minimized the formal charge, which means we've drawn a correct Lewis structure. So for IF4-, which is this compound right here, this is the skeleton structure for it. So you see that we have a negative charge on this compound. And so if you add up the total number of valence electrons, you'll get 35 plus this extra electron. So remember, this negative charge represents 1 extra electron, which brings our total from 35 up to 36 because we're adding it on to the total. So using our normal bonding conventions, this is a case where iodine, since it's the central atom, is going to break its normal pattern and have those 4 single bonds. But fluorine is going to retain its common bonding pattern, so we're going to see those lone pairs scattered around fluorine in this case. Like that. But if you were to add up all of the electrons that we have here, if you were to add up all the lone electrons plus the 2 electrons represented in each bond, you would find that we only have 32 total electrons. And we need 36, so we need 4 more electrons. Double bonding isn't going to help us because double bonding just moves electrons around. It doesn't add any extra electrons. And plus fluorine doesn't want to double bond anyway. So what do you do if you have electrons that you need to account for, you can't make up for it with bonding, and you just don't know what to do with them? Well, if you have those extra electrons sitting around and you've got an element that's beyond the 3rd row, you can just stick those extra electrons as lone pairs on the central atom, like this. So these are our 4 leftover electrons, and we're just going to stick them on the central atom. And iodine is perfectly okay with that because iodine can accept an expanded octet. So iodine is perfectly happy with taking on those 4 extra electrons as lone pairs. And now we've brought our total number of electrons up to 36. But remember that our compound has a negative charge. That negative charge is coming from somewhere. All 4 of these fluorines have a formal charge of 0 because you have 7 valence electrons minus 1 bond minus 6 lone electrons is net formal charge of 0. But what about iodine in this case? Well, iodine also has 7 valence electrons. minus 1, 2, 3, 4 bond lines minus 1, 2, 3, 4 lone electrons. So 7 minus 4 is equal to negative 1. So this negative 1, the formal charge on iodine, is why the compound itself has a negative 1 charge. So the charge of your compound is going to equal the total formal charges on the elements that make up your compound. So in this case, we only have one formal charge, it's on iodine, and it's that negative 1 charge. So this was just sort of an intro to a Lewis structure, sort of showing you how to do it, how to go about doing it. We'll look at line structures in particular in another video where we focus strictly on carbon and carbon-based quote-unquote organic structures, which in Gen Chem are relatively simple, but we'll look at those separately. Hopefully this kind of cleared up how to go about handling Lewis structures in formal charge.